I guess we've already done a couple of simple examples, but I want to do one more example. So, a uniformly charged sphere, solid sphere, has total charge Q and radius R. What is the electric field everywhere? Okay, this is not meant to be a difficult problem. I'm going to add some stuff to it in a bit, but let's start with that. So we've got radius R, it's got a charge Q, which is evenly distributed throughout, so that the charge density of the sphere is Q over the volume of the sphere, which is 4/3 pi r cubed. Okay, so that's charge density, something we're going to need later. But that's what it tells us, that it's uniformly charged. It's got a density, charge density in any little piece equal to Q over 4/3 pi r squared. Total charge divided by total volume is the charge of any piece divided by the volume of any piece. Okay, so let's just think about what is the field outside of that sphere. The field outside of that sphere at any radius, whoops, that's meant to be symmetrical, at any radius r. So what is the field at r? Well, it just looks like a point charge, right? It's a sphere of charge, which is treated the same as a point charge, or we could do Gauss's law, and you find that the electric field outside of the sphere is kq over, and the sphere itself has little r, so the radius at any point r greater than r for, big R greater than little r, the electric field is also in the radial direction, kq over r squared. Simple, simple. What about for little r greater than big R? Yeah, big R less than little r inside the sphere. So now inside, and this is where we care about the charge density, inside the sphere at some capital R, which is less than R, so for capital R less than R, that Gaussian surface that I just drew, that imaginary surface at capital R, encloses some amount of charge. How much charge does it enclose? So the charge enclosed inside that smaller sphere is equal to the volume of the smaller sphere, 4/3 pi capital R cubed times the charge density. That's the charge enclosed. It's the charge density times the volume. That gives us charge enclosed. And so therefore we can use Gauss's law to just simply say that E times dA, we can skip all the steps getting up to EdA because it's just a spherical symmetry. EdA equals charging, well, here, I mean, we really should do E dot dA equals charge enclosed over epsilon 0. So therefore, E times the surface area of that sphere, 4 pi r squared, equals the charge enclosed, which is rho times 4/3 pi r cubed divided by epsilon 0. So the electric field for r less than little r, for capital R less than little r, the electric field is, we can go ahead and say rho times 4/3 pi r cubed divided by 4 pi r squared, epsilon 0. And actually, we can plug in rho as well. But what's important to notice is to not get confused between your r's and your r's. The variable here is capital R. Little r is fixed. Little r is fixed, right? The variable here is capital R. So it doesn't really matter what rho is. Rho is a constant, just in terms of seeing how the field, what the field looks like. And so I'm not going to plug in rho yet. So what you end up getting is 1 over 3 pi epsilon 0 rho times capital R. So, and we can go ahead and plug in rho. So therefore, E is equal to 1 over 3 pi epsilon 0. How about, no, it's not pi. Wait a second. Wait. I made a mistake. There, I had an extra pi in there. I know we all like pi, but can't have it here. Okay, so rho over 3 epsilon 0 capital R, and then we can plug in rho and find that it's kq capital R over little r cubed. But keeping in mind that all the constants are kq and little r, and so this electric field actually, E as a function of capital R, which is our variable, actually increases. So the electric field increases as we move from the center of the sphere, where it should be 0, out to the edge of the sphere. But then what happens, so that's for capital R less than little r. What happens when capital R is bigger than little r? Then it goes down again, right? So looking back at here, goes down again as 1 over r squared. So the electric field goes down, goes down like that, with this peak being at little r. So as big R gets bigger, the electric field gets bigger linearly and then gets smaller quadratically once we get outside the sphere. That's the first part of that problem. Let's then ask, what is the potential energy anywhere? What is the potential energy, not potential energy, electric potential inside or outside the sphere? Now the thing that I forgot to write down when we were doing the quick review is that electric potential difference is defined as, or is derived to be, I don't know if that's defined as, but anyway, is the integral of E dot dl. That's electric potential difference between, and that's the difference between any 2 points, right, between A and B. So electric potential difference from A to B is the integral from A to B of E dot dl. So what is the electric potential anywhere for this sphere? Well, first thing to recognize is that the electric field, it's E dot dl. The electric field can only changes for the sphere in radial direction. It doesn't change if we move in a tangential direction, right? If we keep an constant r. So this dot product simplifies for this particular, for a spherical distribution to EdR. The dot product goes away, it's EdR. So delta V between any 2 points, A and B, is E dot EdR. So now let's find the electric potential at points B and C, where B and C are some distance r sub B and r sub C away, right? So this we'll call r sub B, and this we'll call r sub C, where the radius of the sphere is r. And remember, what we want to do, the convention, is to say, A is infinity. V at infinity is equal to 0. So delta V is VB minus VA, and VB minus VA is the integral of A to B of E dot dl, or EdR in this case. If VA equals 0 at A equals infinity, therefore we can say VB equals infinity to B of EdR. Okay, now we already found the electric field outside the sphere, so VB is equal to infinity to B, and the electric field at point B, which is KQ over R squared, KQ over RB squared, dr. And so what we get is, so we are integrating R to RB, and so what we end up getting, KQ over R squared dr, K and Q are constants. The integral of 1 over R squared dr is minus 1 over R, and we plug in our limits, and so we get minus KQ over R sub B. Except that I apologize, I made an error. Oh dear. I hope you caught this one. So when I started this problem, I said that this is the definition of potential difference between A and B, the general definition, but I left out a minus sign. So what I left out is the fact that the definition is minus E dot dl, minus, minus, and minus, and minus, and minus, and this is where I got to the end. I'm like, wait a second, but we already said that the potential due to a point charge is positive KQ over R, and that's because I left out, and I didn't get it here because I left out the minus sign. Okay, hopefully you caught that earlier. So that's the potential at RB. Now what is the potential at RC? Now you got to be careful. You can't just say it's KQ, whatever the charge is at that point, or the charge enclosed by that point divided by R, because potential is measured from a potential difference. And the problem is that the potential changes at the surface. So what we need to do is go back and think about, we define the potential. Here, let me try to write this down here. That the potential at C is equal to the integral from infinity to C, or R sub C, of the field dr, but the field changes. It changes at RB. So if we just blindly applied the potential at B to the potential at C as well, we would be wrong. So we have to say, this is actually from infinity to RB, because the field changes of E for big R greater than little r, dr, plus the potential from RB to RC of E for big R less than little r, dr. So that's the potential at C. We have to integrate from infinity to RC. Whew. So what we end up getting is the potential. This actually gives us the potential at the surface of the sphere, which is simply, to RB, not to RB. Sorry, still making mistakes. I apologize. Well, hopefully, and the mistakes are only helpful. To the surface of the sphere. That's where it changes. It doesn't change. It's because I drew this here. That was RB. I drew it at the surface of the sphere, and that was confusing me. The radius of the sphere is little r. So we have to integrate to the surface of the sphere where the field changes, and then we can integrate from the surface of the sphere to RC. Okay, one more time. In order to find the potential at RC, we have to integrate from infinity to RC. But the potential changes at the surface of the sphere, so we have to integrate from infinity to the surface of the sphere, and then from the surface of the sphere to RC. So what we end up getting is what I had said to begin with, is that we end up getting, for the first term, we get KQ over R. That is the potential that we get when we integrate from infinity to R. That would just be taking this here and making RB equal to R, because the electric field is the same. But then it's plus the integral from R to RC of our other field, our field inside the sphere, which was rho over 3 epsilon 0 R. Rho over 3 epsilon 0 R dr. I guess our integration variable is capital R, not little r, because capital R was our variable radius. Okay, so this is correct, and so now we have to do that integration, and let me just do it on a new page. So we can do that integration, KQ over R. And part of my problem here is that I used little r as the fixed radius of the sphere and big R as my variable radius. And we usually do it the other way around, so I don't mean for that to be confusing, but it probably is. I apologize. So we can factor out take out from the integral rho of 3 epsilon 0 because they're constants, and it's just the integral of RdR, which is r squared over 2 evaluated from the surface of the sphere to RC, which is inside the sphere. And so we end up getting that the potential at the point C in the sphere is KQ over R plus rho over 3 epsilon 0. And we evaluate R squared, RC squared minus R squared over 2. And that probably simplifies a little bit, but not a lot. So there you go. That's the potential at the point C inside the sphere. Okay, that's probably long enough. You can do more reviewing on your own when you do the homework, and go ahead and ask questions. Have a wonderful day.